In this part of the Neurocomputers and Deep Learning course related to self-organizing feature maps, you will learn what is self-organizing feature maps, how it is trained for data clustering, and also what is the relation between self-organizing feature maps and k-means clustering. Self-organizing feature maps, also known as Kohonen maps or topological maps, were first introduced by von der Maasburg in 1973 and in its present form by Kohonen in 1982. Self-organizing feature maps is a special neural network that accepts n-dimensional input vectors and maps them to the Kohonen competition layer, in which neurons are organized in an L-dimensional lattice grid representing the feature space. Such a lattice characterizes a relative position of neurons with regards to its neighbors, that is, their topological properties, rather than exact geometric locations. In practice, dimensionality of the feature space, that is, Kohonen layer lattice, is often restricted by its visualization aspect, and typically L is the dimension of the Kohonen layer lattice is set to 1, 2, or 3. The objective of the learning algorithm for the self-organizing feature map neural networks is formation of the feature map which captures of the essential characteristics of the n-dimensional input data and maps them on the typically 1D or 2D feature space. The structure of the typical self-organizing feature map network for L equal to 2 is shown in the figure. Here we have a two-dimensional lattice. The structure of a typical self-organizing feature map network for lattice dimension 2 is shown in the figure. In this example, the lattice is two-dimensional. It has n input nodes and m by m output nodes. Number of nodes, the Kohonen layer, is m by m. Each output node j in the self-organizing feature map network has a connection from each input node I, and wij denotes the connection weight between them. It is the connection from the input I to the jth output neuron. The weights of the connections from the input neurons to a single neuron in the competition layer are interpreted as a reference vector in the input space. If we consider the connection weights of a neuron, it has dimensions same as the input space. So this connection vector representing a point at the input space. That is, a self-organizing feature map basically represents a set of vectors in the input space, one vector for each neuron in the competition layer. So, for each neuron in the competition layer, the connection vector is representing a point in the input space. A self-organizing feature map is trained with a method that is called competition learning. When an input pattern is presented to the network, that neuron in the competition layer having the reference vector closest to the input pattern is determined. So we are looking at the distance between the applied input and the connection vector of each neuron. We are choosing the one having the closest connection vector to the applied input is determined. This neuron is called the winner neuron, and it is the focal point of the weight changes. In pure competition, only the weights of the connections leading to the winner neuron are changed. However, generally, competition is used together with cooperation, such that the connections leading to the neuron in the neighborhood of the winner are also updated. So if this one is the winner, neurons in the neighborhood of that neuron at the output lattice are also updated. The changes are made in such a way that the reference vector represented by these weights is moved closer to the input pattern. So the weight vector gets closer to the applied input pattern. During training, the weights are updated according to the formula Wij at t plus 1 is equal to its value at iteration t plus the learning rate, which is changing in time, multiplied by ith component of the applied input minus the connection weight from the ith input to the neuron J multiplied by the value of the neighborhood function at neuron J at time t, where Wij is the ith component of the weight vector Wj of the neuron Nj, and Ui is the ith component of the pattern Uk applied at the input layer. Nt is the learning rate and Njt is the neighborhood function, which are changing in time. The learning algorithm captures two essential aspects of the map formation, namely competition and cooperation between neurons of the output lattice. Competition determines the winning neuron, D-win, whose weight vector is the one closest to the applied input vector. For this purpose, the input vector U is compared with each weight vector Wj from the weight matrix W, and the index of the winning neuron N-win is established considering the following formula. The winning neuron is the one minimizing the distance between the applied input vector and the weight vector of the neuron J. The neuron minimizing this value is chosen as the winner neuron. In self-organizing future maps, not only the weights of the connections to the winner neuron are updated. Rather, there is a neighborhood relation defined on the competition layer, which indicates which weights of other neurons should also be changed. This neighborhood relation is usually represented as a usually two-dimensional grid, the vertices of which are the neurons. This grid most often is rectangular or hexagonal. During the learning process, the weights of all neurons in the competition layer that lie within a certain radius around the winner neuron with respect to this grid are also adapted, although the strength of the adaptation may depend on their distance from the winner neuron. The effect of this learning method is that the grid by which the neighborhood relation on the competition layer is defined is spread out over the region of the input space that is covered by the training patterns. All neurons Nj located in a topological neighborhood of the winning neurons Nwin will have their weights updated usually with a strength Nj related to their distance Dj from the winning neuron, where Dj can be calculated using the formula Dj is the distance of the position of the neuron J on the lattice and the position of the winning neuron, where pos is the position of the neuron in the lattice. The city block distance L1 norm or Euclidean distance L2 norm can be used as norm. In general, LP norm of a vector Z is given by the formula LP norm of the vector Z is the summation I from 1 up to n absolute value of the ith component of the vector Z with power P is calculated. They are summed up and then the root of power P is applied. In its simplest form, a neighborhood is rectangular. For the threshold neighborhood, the value of the neighborhood for neuron J at time t is defined as it has value 1 if the distance of this J neuron to the winner is less than a defined threshold value for time t, and it is set as 0 if the distance of the J neuron, winning neuron, is greater than dt, where njt is used instead of nj since dt is a threshold value decreased via a cooling schedule as training progress. That means that the size of the neighborhood gets smaller and smaller. For this neighborhood function, the distance is determined considering the distance in the lattice in each dimension, and the one having the maximum value is chosen as the distance j. For L equal to 2, that is on a two-dimensional lattice, and j corresponds to a square around the winning neuron having side length equal to 2 dt plus 1. When threshold neighborhood is used, the weights of all neurons within this square are updated with neighborhood value 1, while the outsiders remaining unchanged. As the training progresses, this neighborhood gets smaller and smaller, resulting in that only the neurons very close to the winner are updated towards the end of the training. The training ends as remains no more neuron in the neighborhood. This figure shows threshold neighborhood narrowing as training progress. Initially, the neighborhood around the winner is larger. However, as time progresses, it becomes smaller and smaller. Suppose that this is the winner, while Nj is in the neighborhood in the beginning. Towards the end, it will be outside of the neighborhood around the winner. Usually, the neighborhood function Nj is chosen as an L-dimensional Gaussian function. Njt is set as exponential minus distance of the jth neuron to the winner square divided by 2 times rho t square, where rho square is the variance parameter specifying the spread of the Gaussian function, and it is decreasing as training progresses. Example of a 2D Gaussian neighborhood function is given in the figure. This is a 2D Gaussian neighborhood function for a 40 by 30 neuronal lattice. There are two phases of operation in self-organizing future maps: the training phase and the clustering phase. In the training phase, the network finds an output node such that the Euclidean distance between the current input vector and the weight set connecting the input units to this output unit is minimal. This node is called the winner, and its weights and also the weights of the neighboring output units of the winner are updated so that the new weight set is closer to the current input vector. The effect of update for each unit is proportional to a neighborhood function, which depends on the unit's distance to the winner unit. This procedure is applied repeatedly for all input vectors until weights are stabilized. The choice of the neighborhood function, the learning rate, and the termination criteria are all problem dependent. The clustering phase is simple once the training phase is completed successfully. In this phase, after applying the input vector, only the winner unit is determined. Here is the summary of the algorithm for training self-organizing future map. Assign small random values to weights j. This is the weight vector for neuron j. J is from 1 up to m. M is the number of neurons in the lattice. In the vector, we have the connection from the first input to jth neuron, from the second input to jth neuron, and from the nth input to the jth neuron. And we have such vectors for each neuron in the lattice. Choose a vector uk from the training set and apply it as input. Find the winning output node nwin by the following criteria. The winner is the neuron minimizing the distance between the applied input and its connection weight. Wj here is the weight vector connecting nodes to the output node j. In the next step, adjust the weight vectors according to the following update formula. Wij at time t plus 1 is equal to its current value plus learning rate at time t multiplied by ith component of the input vector minus ith component of the weight vector of the j neuron multiplied by the neighborhood value of the j neuron with respect to the winner neuron at time t, where ij is the ith component of the weight vector wj, eta t is the learning rate, and njt is the neighborhood function. Repeat steps 2 to 4 until no significant changes occur in the weights. The learning rate eta t is a decaying function of time. It is kept large at the beginning of the training and decreases gradually as learning proceeds. The neighborhood function njt is a window centered on the winning unit n-win found in step 3. Neighborhood function determines the degree that an output neuron J participates in training. This function is chosen such that the magnitude of weight change decays with increase in distance of the neuron to the winner. This distance is calculated using the topology defined on the output layer of the network. Neighborhood function is usually chosen as rectangular or two-dimensional Gaussian or Mexican head windows. Also, the diameter of the neighborhood function decreases in time. In Kohonen network, similar clusters are mapped to the neighboring neurons. If the number of neurons in the Kohonen layer is small, in that case, each neuron representing one or more clusters. If we have large number of neurons in the Kohonen layer, in that case, similar clusters are mapped to neighboring neurons again, but more than one neurons representing the same clusters. For example, these pink neurons representing the same cluster, while these green ones are representing another cluster. So more than one neurons representing the same clusters. Future map formation is critically dependent on the learning parameters, namely the learning rate eta and the spread of the neighborhood function, which is specified by the variance rho square in the Gaussian case. In general, both parameters should be time varying, but their values are selected experimentally. Usually, the training phase is separated into two subphases, which are ordering phase and convergence phase. In the ordering phase, say 4,000 iterations, the learning rate stays close to unity during this phase of the algorithm. The spread of the neighborhood function should initially include all neurons for any winning neuron, and it should be slowly reduced to eventually include only the winner. In the convergence phase, say another 1,000 iterations, the learning rate initially should have the value assigned in the ordering phase, and then it should be reduced slowly to reach the value of, say, 0.1, while the neighborhood function should include only the winning neuron. In self-organizing future maps, the neurons are located on a discrete lattice. In training, not only the winning neuron, but also its neighbors on the lattice are allowed to learn. This is the reason why neighboring neurons gradually specialize to represent similar inputs, and the representations become ordered on the map lattice. As the training progresses, the winning unit and its neighbors adapt to represent the input even better by modifying their reference vectors towards the current input. This topological map also reflects the underlying distribution of the input vectors as it is illustrated in these figures. Here, notice that in this figure, the samples are shown as dots and which are chosen from this rectangular region. Initially, the connection weights of the neurons are small random values, so they are close to the origin. However, as the training progresses, notice that the lattice covers the input space. If the samples are chosen from a triangular region as shown in this figure, in that case, again, the lattice is started with small random values close to origin. However, in time, it expands to cover the region from which the samples are chosen. Rigorous mathematical treatment of the self-organizing feature map algorithm has turned out to be extremely difficult in general. In the case of a discrete dataset and a fixed neighborhood kernel, however, there exists an error function for the self-organizing feature map. The error function is such that we have a double summation here. K is for each cluster, and for each sample belonging to each cluster, we are considering a coefficient alpha for that cluster multiplied by the square of the distance between the sample I and the center of the kth cluster. The weight update rule of the self-organizing feature map corresponds to a gradient descent step in minimizing the above error function. If we compare the error function for the k-means clustering algorithm and for the Kohonen network, we see that the cost function of the self-organizing feature map closely resembles the error equation for the k-means clustering algorithm tries to minimize. The difference is that in the self-organizing feature map, the distance of each input from all the reference vectors, instead of just the closest one, is taken into account, weighted by the neighborhood kernel n. Thus, the self-organizing feature map functions as a conventional clustering algorithm if the width of the neighborhood kernel is 0.